Hi everyone, so let's proceed with chapter 4 on the field effect transistors. So we can see in the figure down there, so basically a field effect transistor can be designed as a discrete device, as you can see on the left there. So these are FETs, and we can see that we has typically three terminals or three gates, we can see there. And on the right here is the cross section of the physical transistor device. So you have covered the bipolar junction transistors in the previous lectures. So in this lecture, we're going to look at the field effect transistors, FET. So what's the difference between FET and BJT? So there are several similarities and differences. Both are transistors. That's the first similarity. But other than that, we can see here that the similarity is both can be used as amplifiers, okay, to amplify our signals, current or voltages. Both can be used as switches to turn or to turn off based on a certain input condition, and both can be designed to be an impedance matching circuit. Okay, and the differences, BJT, we can see here that the BJT is mainly the BJT here is mainly a current control device, so we input a certain current value, and it has a higher gain compared to the FET. The FET is mainly a voltage control device. Okay, so this is the main difference. So voltage control means that we control the output based on a given voltage. We put in certain voltage and we expect a certain amplified input voltage, for example. And it has a higher input impedance compared to the BJT, and more static sensitive than the BJT, less sensitive to temperature variation, and the key point on the last one there is can be integrated more easily on the integrated circuits. So let's see the type of FETs. There are several different types of field effect transistors, FETs. There is a JFET, there is a MOSFET, and a CMOS. And in this class, we're mainly going to be looking at the E-MOSFET, okay, which stands for the enhanced mode MOSFET. So MOSFET is a metal oxide semiconductor field effect transistors. And similarly to BJT, we have we can have an N channel, and we can also have a P channel transistors. So exclusively in this class, we are going to look at only at the enhancement mode MOSFET, and we are not going to look at the CMOS and the JFET type, and even the D MOSFET we're not going to look at. So all our analysis, theory, and all will be mainly on the E MOSFET. So MOSFET introduction, calculators, cell phone, PCs are all using MOSFET. Okay, the MOSFET transistors, and in a typical chip IC, we can have billions of MOSFETs. Okay, so what's the advantage of MOSFET? So we can see here that the MOSFET extremely low input current circuits, reduce in heat dissipation, which is good for mobile devices, and compared to BJT is much smaller. Okay, so the goal of integrated circuit is to fit the maximum number of components in the smallest space possible, and since the FET is smaller than the BJT, we can the MOSFET therefore is more suitable to be implemented as an integrated chip. Some of the MOSFET application that probably you're going to see later on, but for this part of the MOSFET lecture, we're going to look at more on the theoretical side to understand really the internal workings and the analysis of MOSFETs. But some of the applications, 3-channel audio mixer is using MOSFET, silent switching, phase shift networks, motion detection system, any integrated circuits all mainly use the MOSFET. So when handling MOSFET, we have to be careful. MOSFETs are very sensitive to static electricity. The reason is because of the thin SiO2 or the silicon dioxide layer between the external terminals and the layers of the device. Any small electrical discharge can create an unwanted conduction. So when we handle MOSFET, we have to be careful and be aware that we can damage the MOSFET if you are not careful. So always transport the MOSFET in a static sensitive bag. Always wear a static strap when handling MOSFET, and apply voltage limiting device between the gate and the source terminals of the FET, such as a back-to-back Zener, to limit any transient voltage. So let's look at the construction of the E-MOSFET. So on the right side here, we can see this is the cross section. So the main thing here to see is we have the three terminals. So we have three terminals in the MOSFET. We have the drain terminal connected, which is a metal contact. We have a gate terminal and the source terminal, so DGS. And then inside the semiconductor device, we have the N-dope region. Okay, we have the N-dope region. So this is N-type silicon, and we have a P-type silicon, okay, called the P-type substrate, P-type silicon in the body, okay, connected to we have another metal contact, which is a substrate contact. Okay, so essentially we have four terminals, but three main ones: drain, source, and gate, and the body contact as well. Okay. So there is no structure channel. The substrate extends to silicon dioxide. The gate connects to the p-dope substrate via thin insulating layer of silicon dioxide. So here is your silicon dioxide, if you can see here. Okay, so this sort of like a diagonal stripe area there is your silicon dioxide, and here is your metal. Okay, so your metal is connected to your gate, silicon dioxide, and connects to a p-type semiconductor. Okay, which is dope, a p-dope semiconductor, and we have an n-dope semiconductor as well. The n-dope material lies on the p-dope substrate that may have additional terminal called the substrate SS. Let's look at the symbol. Okay, so we have a conventional symbol for the N channel, and we have a symbol for the P channel. We have a simplified symbol for the P channel and the N channel E-MOSFET. So basically in this class we are mainly going to use, mainly see the N channel E-MOSFET using the simplified symbol. So so this symbol is important to know and to recognize, since we're going to be seeing this for quite a lot during this lecture. Okay, so let's see how the E-MOSFET works. So how it works is basically we are going to connect our MOSFET here. So this is our MOSFET, and we have the three metal contacts, three main terminals of the contact: the drain, the gate, and the source. And we provide input voltage. Okay, we provide the input voltage VDS. Okay, and then we're going to find what is your drain current, okay, given the input voltage VGS. So we have a voltage VGS, which is a potential between the gate and the source, and we have VDS, which is a potential between the drain and the source. And then based on a certain value of VGS, okay, based on a certain value of VGS, we can then obtain the current ID, okay, the current ID going like this, okay, and we can also calculate and see what is our VDS. Okay, so so if we look here, when a plus voltage channel is applied to the gate, the N channel E-MOSFET responds in the same manner as the D-MOSFET. Okay, we are not looking at the D-MOSFET. As shown in the figure, the plus gate voltage forms a channel between the source and drain by the depleting area of the valence bond holes. So there's some theory there. Essentially what's going on is when we apply the VGS, okay, when we apply the voltage on the gate, then something happens along the channel. Okay, basically we are going to create a conducting channel underneath the gate terminal, and this conducting channel will allow the current ID to pass through. Okay, so essentially that's the idea. If we apply VGS 0, okay, very small VGS, so no value there, then this one will be a p-type semiconductor, and ID will be essentially 0. Okay, so let's see the transconductance curve. So here, for example, we can see that what is our ID, okay, given a certain value of VGS. So we're looking at ID and VGS. So this is the ID VGS curve. Okay. And one important point here is your VGS TH. Okay, VGS TH down here. Maybe it's not so clear down there. So it's a VGS TH, which is called the threshold voltage. Okay, it's a very important concept. So what is a threshold voltage? The threshold voltage is the point at which the device is turned on. So if you want to turn on your transistor, how to turn on your transistor is essentially you just give your VGS greater than your threshold voltage. So let's have a quick draw here. So something like this. Okay. Okay, so this is your drain, the source, and the gate terminal. So ID is going like this. Okay, so we are looking at ID and VGS. So how to obtain ID? How to obtain ID is by applying your VGS greater than VGS TH. So as long as your VGS, okay, is greater than VGS threshold, therefore you are going to get certain ID, and the more value that we provide for VGS, then the higher is your drain current ID. So summary of the basic E MOSFET: the VGS is always positive. Okay, it is 0 and above for N channel. As VGS increase, ID increase. We saw this already. Okay, so the VGS ID curve. As we increase our VGS, the drain current also increase. As VGS is kept constant and VDS is increased, then ID saturates and the saturation level VD sat is reached. Okay, so here we are looking at VDS and ID. So again, to understand the flow here. Okay, so ID, remember, going like this. So this is your drain, your source, and your gate. Okay, so what happens when we increase VGS? Our ID is going to increase according to the graph. And what happens if we increase VDS? Okay, what happens if we increase VDS? So as we increase VDS for a given VGS, so let's say VGS is 8 volt. Okay, certain value of VGS, and as we increase VDS, we reach a saturation current. So this is your ID sat. Okay, IDSS. Okay, so there are several important equations that we need to know. How to find your ID given VGS. Okay, so for example here, given a certain value of VGS, what is your ID? So this is your equation here that we need to know and really need to understand. So ID equals to K VGS minus VT squared, where VT is your threshold voltage. So VT is in fact your VGS TH lah. Okay, different book using different notation. Sometimes we call it VT, sometimes VGS VT, VGS TH. Okay, so ID equals to K VGS minus VT squared. And what is your K? So K here is a constant that can be determined by using values at a specific point, and the formula K equals to ID on over VGS on minus VT squared. Okay, or VGS T squared. And VD sat can be calculated by VGS minus VT. So VD sat is actually here. Okay, this is your VD sat. Okay, and it's different for different VGS. So as you see here that depending on your value of VGS, okay, you're gonna have a different VD sat. Okay, so VD sat is right there, and here is your ID sat, IDSS. Okay, and okay, so three important equations that we need to know when we do some analysis later on. So as a summary again, we are seeing this that again let's take our our MOSFET here. Okay, gate, drain, and the source, and here is your ID. Okay, and here is your ID VGS. Okay, so ID VGS curve. So we are looking at how your drain current ID will change according to the applied VGS. Okay, so what if you put your VGS very small? Okay, if you put your VGS very small right here, for example, you put your VGS, your drain current is going to be 0. Okay, so as you increase your VGS, we can see that the current ID that goes from the drain to the source actually increase exponentially. Okay, so P-channel MOSFET is similar to the N-channel. The difference is that the threshold voltage VGSTH is now negative. Okay, instead of 2 volts, it's negative 2 volts, and we have to apply a negative voltage to turn on the device. And another main difference here is a P-type. So you can see here is a P-type, the N-type. Okay, so the terminals connect to the P-type semiconductor, and the body is on the N-type semiconductor. Okay. Okay, so I think this is it for this part of the lecture. We'll continue on the next one in the next video.